Welcome to digital design. The first surprise is that digital systems are not made of abstract zeros and ones floating in space. They are made of real voltages, moving through real wires. A zero is usually a low voltage range, a one is usually a high voltage range. Digital design begins when we agree to treat messy analog voltage as a clean decision. Today we build that agreement. Voltage becomes a bit, bits feed logic gates, and gates become the building blocks of a computer. Here is the core contract. The input does not ask for exactly 0 volts or exactly 3.3 volts. Instead, it uses thresholds. Below the low threshold, the input is accepted as 0. Above the high threshold, it is accepted as 1. Between those two thresholds, there is a forbidden or undefined zone. That middle zone is not a third logic value. It is a warning sign. Do not design a circuit that depends on a voltage landing there. Once the threshold decision is made, the circuit can forget the exact voltage for a while and think in bits. A logic gate is a tiny rule machine for bits. An inverter turns 0 into 1 and 1 into 0. An AND gate turns on only when all its inputs are 1. An OR gate turns on when at least one input is 1. The deep idea is abstraction. We hide voltage details behind a bit contract, then build bigger rules out of small, reliable rules. Now let us solve a real-style threshold example. Suppose a 3.3 volt digital input has two limits. VIL max is 0.8 volts, so anything at 0.8 volts or below is safely low. VIH min is 2.0 volts, so anything at 2.0 volts or above is safely high. Three measurements arrive at the input: 0.4 volts, 1.2 volts, and 2.8 volts. Which ones are safe zeros or ones, and which one should make us nervous? Start with 0.4 volts. It is below 0.8 volts, so it is a safe zero. Its low noise margin is 0.8 minus 0.4, which is 0.4 volts. Now 2.8 volts. It is above 2.0 volts, so it is a safe one. Its high noise margin is 2.8 minus 2.0, which is 0.8 volts. But 1.2 volts sits between 0.8 and 2.0. That is not a safe zero and not a safe one. In a digital design review, that value is a bug report, not an answer. This is why digital design scales. At the bottom, physics gives us voltages. Thresholds turn voltages into bits. Gates turn bits into logic. Multiplexers and adders turn gates into useful choices and arithmetic. Registers remember bits over time. Finite state machines control sequences of decisions. And when these pieces are organized carefully, we can build processors and memory systems. Every level is a promise to the level above it. So the first mental model is simple and powerful. Digital does not mean the analog world disappeared. It means we build a disciplined interface on top of it. Use safe low ranges for 0, safe high ranges for 1, and avoid the undefined middle. Next, we will learn the number systems that make those bits useful: binary, hexadecimal, and how to read bit patterns without getting lost.